again, now I change, let's say, the specimen, the problem, but we continue working on fatigue. In this case, the presentation is entitled Multiaxial Fatigue Life Predictions of Hot Dip Galvanized Steel Bolted Joints under different configurations and load conditions. And in this case, we conduct this work with colleagues from the University of Porto, from the Czech Technical University in Prague, and also from the University of Mondragon in Spain. The presentation is divided as follows. As always, I will start with a brief motivation, then with the experimental campaign, followed by a numerical approach, in which I will explain the finite element models that we developed for this work, and also the framework we prepare to compute the multiaxial fatigue life of these joints. Then we will continue with the numerical results. I divided also in 2 points. First, the contact analysis, and then we are going to see the fatigue life predictions. As usual, I will finish with some conclusions of the work. So let's start with the motivation. So what we have to take into account is that the main motivation of this topic comes from the current situation, let's say, in the industry, where there is, let's say, a widespread use of different kind of structures which use bolted joints. Here I put some examples, for example, solar industry, pallet storage systems. I show you here two different joints. This one is commonly used for solar structures, very interesting joint because it's not a calibrated fault, it's a slotted bolted joint, and it has some difference with conventional joints. And also here we can see, for example, a common bolted joint used in the rack industry. What is maybe more interesting is that these joints, all the joints I show you here, are commonly used commonly made with cold form hot dip galvanized steel plates. And this kind of details, this kind of material is not yet included in the, for example, last version of the Eurocode. So when we try to design some components, some structures, some systems which include these kind of connections, we do not have a recommendation, let's say, for that. So taking all these points into account, in some previous works, the static behavior of this kind of bolted joints was analyzed. Here I show you the reference of the work and also some images of the experimental setup that the colleagues from Porto developed to test this kind of joints. Also, the fatigue behavior of these joints was also analyzed and compared with the closest curve in the new proposal of the Eurocode. Here I show you a figure with the results, and maybe you can see. I'm not sure about this, but maybe you can see the curve, the new curve proposed in the new version of the Eurocode, which give us conservative results, but maybe it's useful for this kind of joints. Also, in the same article, a local approach was proposed based on the modified Monroe equation to predict the fatigue life of these components. Here you can see the predictions of that equation, but nevertheless we can see that there is some discrepancy in the prediction, and we are obtaining some not safety, let's say, results for some of the configurations. So with all this in mind, maybe again some questions may arise. No? So nevertheless, these discrepancies or the discrepancies observed and the multiaxial stress state to which these joints are subjected lead us to believe that maybe it may be necessary to implement more advanced fatigue criterions to predict the fatigue life of these joints and verify if these criterions were capable or not of predict the failure of the joints. That's the main objective of this work. Regarding the experimental campaign, we are going to validate or analyze two different models. The first one, and in the following, I will refer to it as a model M12 1+1. which has different components: 2 bolts, 2 washers, 2 nuts, and two plates and 2 covers made of S350 GD steel. And we have different configuration, what we call the snook type configuration, in which we apply the 25% of the standard recommendation for the bolt preload. We also have the preload configuration in which we apply the maximum preload that the standard recommends us for this kind of bolts. And we also analyze different stress ratios for the snook type configuration. Regarding the other model, in this case, we have the same type of bolted joints, but the configuration is a little bit different. We have 8 bolts, 8 nuts, and 8 washers, and we still have 2 plates and 2 covers. In this case, it's important to point out that we only have one configuration, which is the snook type. So regarding the numerical model, you can see here a general overview of the 2 models. Now, for the sake of simplicity, I'm going to show you, or let's say to focus only on one of them, but the idea and the strategy is the same for the both models. So we can see here the boundary conditions we use for this model. As you can see here, the model is we only simulate a quarter of the model. We can see that we have one fixed end, then we have the 2 covers, the plate, the bolted joints, and the axial load. And here I show you an image of the local mesh we have in the plate, in which we are going to compute the different multiaxial fatigue criterions, and in which we are going to analyze also the contact status of the joint. Here you can see also the type of the reduced integration elements we are using, and the mesh is like 0.3 millimeters. The local mesh size. Regarding the material behavior, this is the stress strain relationship for this material that we obtained from experimental test, and we introduced this in the elastoplastic finite element model that we have developed, in which we include also the multilinear kinematic hardening. Regarding the analysis configuration, I think it's quite interesting because although it's not nothing new, sometimes it's quite difficult to see which is the configuration of this kind of simulations when we read articles, and I think it's quite interesting for us to show it here. So in the first step of the simulation, what we apply is the bolt preload. Then in the second step, we apply the maximum experimental, the maximum load that we have in the experimental test. And in parallel with that, what we do is fix the bolt length to ensure that we have the same bolt preload. And in the last step of the simulation, we apply one fatigue cycle. So this is important because we apply this. We have to simulate each of the, let's say, of the tests that we have experimentally with this approach. Here you can see the maximum. Well, the points that I show you in the slide are the maximum fatigue test load, and here is the minimum value. And also the contact type is a penalty. We use the penalty method with the coefficient of friction 0.12, which we extract from the experimental results. In order to compute the multiaxial fatigue, or just to use the different multiaxial fatigue-like criterions for this kind of joints, the first step or the first thing that we have to do is to perform the simulations of each of the specimens, let's say, and also in parallel we need the fatigue properties of the steel. In this case, as I comment, we are using an S350 GD steel, and the problem with this material is, well, maybe it's not a problem, but the thing is that this material is only supplied as thin plates. So in order to characterize its fatigue behavior is quite difficult to obtain, for example, the low cycle fatigue and the high cycle fatigue properties that we need for these multiaxial fatigue criterions. So what we have done in this work is using the fatigue properties and the fatigue coefficients derived for the S355, which in terms of mechanical property and chemical composition is maybe the most similar structural steel that we can use for this problem. After that, we develop a Python subroutine which allow us to compute and to find the critical plane for these three different criteria, the Watson-Topper, the Fatemi-Sossi, and the McDiarmid. And with this, we are able to obtain the parameter distribution and the fatigue loss predictions for each of the bolted joints analyzed here. So now let's move to the numerical results. Again, for the sake of simplicity and for the time we have, I only select the results for one of the, let's say, for the M12 1+1 joints. We also have the results for the other model, and maybe we can discuss it later. But in any case, I show you here the contact status for the preload configuration, and I have selected three different variables, which are the contact status, the contact pressure, and the frictional shear stress. And we can now see how this variable change, how the maximum value of this variable change as we increase the maximum axial load. What we can see, for example, here for this configuration is that there is not a clear change in the contact pressure or in the frictional shear stress. We also represented these results for the path I show you in the slide, and we can see that the maximum value is achieved for the specimen subjected to the minimum axial load, but the difference is not very significant in comparison with the other specimens. We can see, for example, the same for the frictional shear stress, where the minimum value is obtained again for the minimum axial load. We can do the same, for example, for the snug tight configuration, and we can see that here there are some, let's say, we can appreciate some change, some local change in the contact pressure and in the frictional shear stress as we increase the maximum axial load. But again, these values are not very significant, and when we represent or when we extract these values in the path I show you in the slide, because in that path is in which we observe the crack to initiate in that surface of the specimen, we again see that there is not a clear or a significant change. Although it's quite curious that in this case the maximum value is obtained for the bolted joints subjected to the maximum axial load instead of the minimum as in the preloaded bolted joints. And the same idea can be observed for the frictional shear stress. But now let's move to the next step, which is maybe the most important for us now, which is to the multi-axial fatigue loss computation. And again, I would like to show you the distribution of this parameter for some of the configuration and compare it with the crack location that we have observed in the experimental results. So let's start again with the preload configuration. Like you can see here, we do not have images or let's say or macrographies for all the specimens, but you can see here for some of the configurations the crack location and the distribution of the parameter close to the let's say to the hole, no? In this case, as we increase the load, the crack location changes, but also change the distribution of the parameter. Here, it's I think one of the points that we have to take into account with these numerical models is that in this case the bolted joints the holes are punch holes. So I think that the manufacturing process, let's say the numerical model is not seeing the manufacturing process. So in terms, for example, of residual stresses or other kind of not problems, but situations that we induce during the machining process, the numerical model is not able to capture that information. So I just want to say this because I think it's important to take this into account. Also, if we now move to the snug tight configuration, I show you some representation of the crack location again and the distribution of the parameters. And as we increase again the load, we see again a change in the crack location. Now it's close to the hole center, and in this case, the parameter distribution is maybe more close to the crack location. But what is maybe interesting now is to try to predict, as we have now the distribution of the parameter, we also have what for example, the Smith-Watson-Topper N representation. Know that to derive this figure or this representation, we need the fatigue properties of the material that we can use here. And I would like to say that also these fatigue properties are very dependent of the experimental campaign you select from the literature. And you can see that there is some, if you use, for example, other values that are also available in the literature, you are going to see that there is a change in this curve and also a change in the prediction. In any case, assuming that these values are correct, these are the results that we are obtaining for the Smith-Watson-Topper parameter. What we can see is that the Smith-Watson-Topper, well, we can see that the most, let's say, or the less conservative results are obtained for both the configuration with preloaded volts and lower axial load, and also for the Snook type configuration with a stress ratio equal to 0.3. For the rest of the results, in this case, the Snook type configuration, we are obtaining conservative results with this approach. When we move to the Fatemi-Sossi model, the results are the following. We can see that, again, we are obtaining the less conservative results are obtained for the Snook type configuration under a stress ratio equal to 0.3. And we are obtaining conservative results for both the for preloaded joints and also for the Snook type configuration with different stress ratio equal to 0.1 and 0.5. If we move now to the McDiarmid model, we always obtain a conservative results for this case. So with this, I would like to finish with some conclusions of the work and also some future lines, which I would like to explore regarding these voltage joints. So the first thing is that, well, we have analyzed the fatigue behavior of this hot dip galvanized voltage joints with different configurations in terms of volt preloads and geometrical configurations. We also develop a finite element model to assess the fatigue behavior of these joints and ad hoc abacus, Python subroutine to compute the fatigue life with different multiaxial fatigue criterions. And what we have seen is that the Smith-Watson-Topper parameter leads to less conservative results, while the predictions achieved with McDiarmid or even, well, especially with McDiarmid or even with the Fatemi-Sossi approach, are always on the side of the security. No? Regarding the distribution of the contact variables, there is not, let's say, a notable difference between the different configurations. And as future works, one of the things in which we are now working is to implement the methodologies that we have seen in the previous presentation regarding the scale effect to this kind of joints. So we can, for example, transfer, if we have let's say, the primary Smith-Watson-Topper field, try to predict the fatigue life of this kind of joints and see if in that way we obtain better results than the ones that we have seen now. And well, I would like to finish with this photo of my village in Asturias, and that's all from my side. Thank you so much for your kind attention.